Law of conservation of mechanical energy. We said last time that the total energy, total mechanical energy, which means potential energy plus kinetic, in a system stays constant as long as what happens? What was the condition? Total energy stays the same, right, Adam? As long as there are only conservative forces acting on the system. Yeah, here's what we're saying. We're saying that the potential energy plus the kinetic energy that we start with, this is how we write it as an equation, PE1 plus KE1, that's total energy that we start with, is equal to potential energy plus kinetic energy that we end up with, PE2 plus KE2. It just says energy equals energy. The total amount stays the same. But there's a catch. And the catch is, Adam, what you said, this only works if there are no non-conservative forces. The forces have to be conservative for it to work. And that's what we were talking about at the very end of class last time. What do we mean by a conservative force? And what do we mean by a non-conservative force? And last time I gave you one example of a conservative force. Remember which force we said last time is conservative? Right, Liz? Gravity. Yeah, gravity is one example of a conservative force. Now, why did we say gravity was conservative? You remember what our test was? Remember our piano moving example that we gave? We said forces are conservative forces if what's true about the work that they do. Right, Jack? Yeah, the work is the same no matter the path that you take to get from the starting position to the ending position. So we said if you're climbing a mountain, it really doesn't matter if you're working against gravity, whether you go straight up or you take a zigzag path. Either way, you do the same amount of work against gravity. So we said conservative forces are forces whose work is path independent. The work of conservative forces does not depend on path. And we said for gravity, if the force is really big when you go straight up over the mountain, then the displacement's real small. If the force is really small for the switchback zigzag path, then the displacement is real large, so the work's the same either way. Now how about friction? Is friction a conservative force? Let's say I take this eraser and start out with it at this end of the lab table, and I want to push it to the other end of the lab table. You know, one possible way to do that would be a straight line path right across the table. Another possible way of getting there would be to zigzag back and forth across the table, maybe even backtrack a little bit, eventually get to the other end of the table. All right, so in one case, we're just taking the eraser in a straight line. The other case, we're going kind of all over the place, but eventually winding up at the same place. Is the work the same both ways? Is it just like gravity where in one case you have a small force and a big displacement? In the other case you have a big force and a small displacement? Hey, Molly, you're shaking your head no. Why not? Yeah, either way it's the same force of friction, isn't it? Same force of kinetic friction either way. It's just that in one case you go not so far, and the other case you go a lot further. So, Molly, you're saying the work's going to be greater which way? Yeah, when you wiggle all around, that zigzag path, a lot more work than the other way. Therefore, friction is not a conservative force. Friction's a non-conservative. Friction would be one example. Because friction, the work that it does, depends on the path that you take. Can you think of any other forces like that, that the work that they do depends on the path you take to get there? What's another very common type of drag force besides sliding friction between two surfaces? Right, Alexis? Yeah, air drag. Air resistance, another good example of a non-conservative force. Let me give you another way of thinking about a conservative force. Conservative forces, we said the work is path independent. Doesn't matter how you get there. Another way of thinking about it, conservative forces are forces whose work always lowers the potential energy of the object. If a conservative force does work on you, it's going to lower your potential energy. For example, if I take a ball and I simply drop it, if I drop a ball, does any force do work on it as the ball falls? Any work being done on the ball as it falls? Yeah, gravity does work, doesn't it? Does gravity do positive work or negative work on the ball as it falls? It does positive work. Yeah, the work done by gravity is positive on that ball. But as gravity does that work, what's happening to the potential energy of the ball? As it falls down, it gets lower and lower and lower. Its potential energy is getting less, getting smaller. Whenever a conservative force does work on something, it always lowers its potential energy. That's a way of telling that it's a conservative force. All right, so how about elastic forces? If I take this rubber band and I stretch it, all right, I'll stretch it and point it at Gerov, all right? Now, this elastic force is about to do some work on the rubber band. As it does that, what happens to the potential energy of the rubber band? I start with it stretched out, right? Then the conservative, I won't point it at you, Gerov. Then the conservative force does some work. I shoot it across the room, right? Potential energy of the rubber band got higher or lower? It got lower. Yeah, elastic forces are another example of conservative forces. When a spring or a rubber band acts on something, that's a conservative force because when it does its work, it lowers potential energy. One final thing we can say about conservative forces is that conservative forces are forces that depend only on position. They depend only on the position of the object. The gravitational force acting on you depends on your position relative to the Earth. If we take you to an altitude of 10,000 feet, the force is going to be a little bit different. If we take you 2 miles above the surface of the Earth, the force is going to be different yet. Likewise, elastic forces for this rubber band, the force that the rubber band exerts depends on the position. See, that's not true for friction. Frictional force doesn't depend on where you are. It makes no difference where you are on the table, the frictional force is the same. Whereas for conservative forces, it does depend on the position. Those may just seem like some meaningless definitions, but they're going to be really important because when we go to apply this law of conservation of energy, it only works if there's no non-conservative forces. So we have to be able to identify which we're dealing with. Let me give you one more example. Let's say that bicycle is being pedaled down the road by Elena, right? So there's a force exerted by her feet against the pedals. Conservative or non-conservative? Does Elena's force against the pedals, does that fit this definition of conservative force? Is it path independent, its work? Does her work result in a lowering of potential energy of the bike? And does the force that she exerts depend only on her position? Adam, you're saying, no, it doesn't. I mean, she's going to apply whatever force she wants to apply, right? And it's not going to depend on position necessarily. It's going to depend on whatever she wants it to be. Right? That's a non-conservative force. Okay? Well, let's apply it to some problems. What we're going to find is that law of conservation of energy can do two things for you. Number one, it can take some problems that you already know how to solve other ways and solve them more easily for you. And number two, it can take some problems that you can't solve any other way and make them very easy. Once you get onto this, you'll try to use this wherever you can because it's a very easy, convenient way of solving problems. And let's start out with something that was a problem that you could have done back in October. Right, a free fall problem, very simple problem. We take a ball and we drop it from rest. And we want to know how fast it's going just before it hits the floor or just before it hits the ground. And let's say we're dropping it from a height of 2 meters. Now, earlier in the year, to solve this problem, you would have looked through all those different kinematics equations, and you would have said, well, how do I get final velocity if I know initial velocity and displacement and acceleration? And you would have rooted through to get the right equation. Using conservation of energy, there's only one equation you ever have to use. That makes it nice. Every single problem, you're going to start out with PE1 plus KE1 equals PE2 plus KE2. Total energy stays the same. Now, what assumption are we making about the ball as it falls through the air in order to write that equation? We're automatically implying that there can't be any, right, Jack? Any drag forces of any kind. That's right. So evidently this thing's in free fall. But that's always the assumption we made before anyway, wasn't it? I mean, we assumed it was falling at negative 9.8 meters per second squared. That's really only true for free fall. No air drag. All right, so let me give you a kind of a step-by-step process for energy problems. First, you write the equation like we did. Secondly, number the positions for the object. Where we start, we're going to call that position 1. And where we end up just before it hits the floor, we'll call that position 2. So we're saying potential plus kinetic up at the top has to equal potential plus kinetic down at the bottom. And then what you want to do is you want to look for any terms in that equation that are 0. Because if they're 0, we want to get rid of them. So first of all, think about your kinetic energies. Is the kinetic energy of that ball at either of those two positions 0? Right, Molly? At the first position it's 0. We'll cross it out. And why is that? Because it's not moving. We're dropping it from rest. Yes, there's no kinetic at position 1. And how about your potential energies? Right, Tyler, what do you want to do? You're saying no potential at position 2. We're going to cross that out. And that's true as long as we call position 2 our, what was the name for that? Remember what we call the place where we're defining the potential energy to be 0? Yeah, we call that our reference platform. So really, Tyler, in your mind, you're saying we're going to call the floor the reference platform. We're going to define that as being 0. Now, could have you made position 1 your reference platform instead and crossed out PE1? Yeah, you could do it that way, but what would you have to be careful about if you did it that way? If you made position 1 your reference platform, then what kind of potential energy would you have at position 2? You'd have negative. Most of the time, we don't like to deal with negative numbers. So a rule of thumb is make the reference platform the lowest point in the problem. If you do that, then you won't have to worry about the negative potential energies. All right, once you've done all that, it's just a matter of plugging into the equation. Potential energy at 1 is mgh1, because potential energy is mgh. Kinetic energy 2 is 1/2 m v2 squared. And since m is on both sides of the equation, we can divide that out. And we're left with v2 is just the square root of 2g h1. And that's just the square root of 2 times 9.8 meters per second squared times the 2 meters. So whatever the square root of 4 times 9.8 is, which is about 6.26 meters per second, that's our final speed. That's a problem that you, like I said, could have done back in October just using one of your kinematics equations. I'm not sure that this method of doing this problem is any easier. It's just a different way of approaching it. So far, so good? All right, the next problem I want to show you is one that, again, you could have done, thanks, you could have done earlier in the year, but this time energy is going to make the problem a lot easier than it was earlier in the year. So, let's look at an inclined plane problem. All right, here's an incline. We're going to make that a 37-degree incline. And here's the scenario. We have an object at the bottom of the ramp, maybe a box of some sort. It's already moving. All right, it's already in motion. Somebody gave it a kick or something. It's already traveling up the ramp, moving at 10 meters per second. Now, we all know as it goes up the ramp, what's going to happen to its speed? Yeah, it's going to get slower, 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 slower. Eventually, it's going to do what? Yeah, it's going to stop and come back down again. And here's the question. How far up the incline does the box travel before it stops and comes back down? How far does it make it up the incline? And let's just arbitrarily say that it makes it to right about here. What we're after is what's the distance from where it started here up to there. That's the goal, to find that distance there. How far does it travel up the incline? And we're going to make the assumption that there's no friction or air drag, because if there were, then we wouldn't be able to use conservation of energy. Well, there is a way to modify that, but we're going to learn how to do that maybe next week. Right? For right now, we're just tackling the cases where we don't have non-conservative forces. I want you to think about how you would have solved this problem back in November. It would have been long. Yeah, what would have been the first step? You said it, Austin. You would have had to draw a free body diagram. Let's think about that. The whole point of drawing the free body diagram would be so you can calculate what for the box? The net force, so you can calculate its acceleration. And then finally, once you get the acceleration, then you still have to use one of those kinematics equations to relate the initial velocity, the final velocity, and the distance. By the way, what's the final velocity of the box? Yeah, 0. So it's at least 3 steps. You need a free body diagram, you need Newton's second law, find the acceleration, then find a third equation to relate the acceleration to the distance. Would you like to do it in one step? So would I. Right? Energy conservation. Let's call this position 1 where we start, and position 2 up here at the top. And again, we know that PE1 plus KE1 has to equal PE2 plus KE2. Energy has to be conserved if there are no non-conservative forces. The first plus sign doesn't look like a plus sign. Well, now it does. Gee. Major plus sign. Let's fix that up. Where did that other jump to? Just a little. You get it there? You know what I think it is? It's a different level of the board there. There we go. Good enough. What's going to be 0? Right, Liz? All right, the original potential energy is going to be 0. So you're saying that you're going to make this level your reference platform, since that's the lowest point in the problem? Makes sense. So we get rid of PE1. Anything else? Hey, Molly? The final kinetic, because up there at the top it has to stop once it reaches its furthest position it's ever going to go, up the ramp. And then we're just left with kinetic at 1. Kinetic at 1 is 1/2 mv1 squared equals potential at 2, which is mg h at 2. And we can get rid of the m's. They cancel out. So 1/2 v1 squared equals g h2. Now we know V1, so we can solve for h, but is h what we're after? We're after d. We're after the distance along this hypotenuse. H is going to give me what? That's height. Yeah, that's going to be the height from the reference platform up to position 2. So h would be this distance right here. But if I solve for h, how can I relate that to d? Well, I could use Pythagorean theorem, but to use that I'd have to know the bottom part of the triangle. I can use trig. Yeah, I can say I know the sine of 37 degrees is equal to opposite h over hypotenuse d. Therefore, h is d times the sine of 37 degrees. Let's just take that and put it in for h, since h is what we're after. So 1/2, since d is what we're after, rather, 1/2 v1 squared is equal to g times, for h we're putting in d times the sine of 37 degrees. And here in one step, or one equation, it took us a couple steps to work through the equation, but we have everything we need. Plug in the numbers. 1/2 v1 was 10 meters per second. Square it, that's equal to g, 9.8, times d times the sine of 37 degrees. And it's just a matter of solving for d. So half of 10 squared, which is 100. If I divide that by 9.8 and divide that by the sine of 37, looks like this thing's going to go about 8.5 meters up that ramp, if my math is right there. Questions about the problem? Again, that's a problem that you could have done before, but it would have taken you a lot more work before than Energy Methods makes it easier. The next one we're going to look at is one that you couldn't have done before. In fact, the majority of this stuff you're going to be doing at Six Flags, if you elect to go on that trip, is stuff where you have to use conservation of energy. Because when you're looking at a roller coaster, here's a side view of some track. Conservation of energy is pretty much the only game in town. And let's see if you can see why here. Let's say that the height of our first hill is 35 meters. And then this next hill, this isn't drawn to scale, but I'm going to make the next hill 20 meters above the ground. And we're going to have a simplified roller coaster for now, single car, instead of a whole train. Now, if this is the very first hill, are you typically moving real fast at the top of that first hill? Now, usually real slow, right? And that chain pulls you very, very slowly up to the top of that first hill. Let's say by the time you get there, you're going 5 meters per second, which, if anything, is probably faster than what you typically go. And here's the problem. I would like to figure out, I'd like to predict what your speed is going to be at the top of the second hill, just knowing what it is at the top of the first hill. Now, we're going to make some assumptions to be able to use conservation of energy here. We're assuming what's true about our track and roller coaster. Yeah, no non-conservative forces, and the major non-conservative forces you would have here would be friction between the coaster and the track and air drag. Now, why couldn't you solve this problem using free body diagram and Newton's second law? And we said for the ramp you could do that. Get the acceleration, use the acceleration. Why couldn't you do that here? You don't have a constant slope. It curves, right? So the direction of the weight parallel would keep changing, which would mean what's true about the acceleration? It keeps changing, doesn't it? It starts out at 0 at the top of that hill, then it gets bigger as the hill gets steeper, then it gets smaller as it gets less steep. That would be a nasty problem to solve with Newton's laws. In fact, the only way you could do it is with calculus, dividing that track up into an infinite number of little pieces, and each different piece would have a different acceleration. That'd be a mess. But with energy conservation, it's really a piece of cake. Position 1, position 2. Total energy at position 1 equals total energy at position 2. And what do you think, Dennis? Anything 0? Anything we can cross out? You want to make position 1 your reference platform? Want to try again? I mean, you could, but then you'd have negative potential energy at position 2. That's what I would do. I would make position 2 my reference platform, cross that out, and I'm just going to make myself a little note on here so I don't forget. I'm running my reference platform right through that second position, just because that's the lowest position of the two that I'm interested in. Now, could you make the ground your reference platform instead? Yeah, you could do that, but then you'd have more work, because then you wouldn't be able to cross out any terms in the equation. Easier way of doing it. All right, once you've done that, potential energy at 1, that's mgh1, plus kinetic at 1, 1/2 m v1 squared, equals kinetic at 2, 1/2 m v2 squared. Do I need to know the mass of the train and the riders and all that kind of stuff? That's right, just a single car, not a train. But no, I don't need to know it. The mass cancels out. So I'm just left with g, 9.8 meters per second squared, times h1. 35 meters? Right? It's the height of my first toe, isn't it? And you already saw me pick up the eraser, so you know it's not right. But what's wrong with the 35 meters there? Hey, Randy? Yeah, my reference platform isn't on the ground. It's already 20 meters up. And h in that equation is always the height relative to that reference platform, which means I got to make it what? Right, Kyle? Just 15 meters. That's right, because we're 15 meters above the reference platform. Right? Plus 1/2 v1 squared, v1 was 5 meters per second, is equal to 1/2 v2 squared, the thing we're trying to find. So again, in one step, we can get our answer. Left-hand side, 9.8 times 15, plus 1/2 of 25. On the left-hand side, you get about 159.5 when you work that out. And that's equal to 1/2 of v2 squared. So I'm going to have to multiply by 2, and then take the square root of all that. And if you do all that, you get v2 is about 17.9 meters per second. So at the top of the second hill, that's how fast you ought to be going. Now, in real life, if you actually measured how fast you're going at the top of that second hill, would you expect that answer to be right on? Now, you'd expect your actual measurement to be a little bit lower than this, because in real life there is friction and air drag. And friction and air drag is going to take energy away. And the further you are from position 1, the more energy it's going to take away. In other words, this prediction would be pretty good if position 2 is close to position 1. But if you're trying to predict what's going to happen at the very end of the track, 30 seconds into the ride, it's not going to be so good, because that was even more time and more length of track for non-conservative forces to do negative work. Well, let's add a part B to the problem. This is a low-budget roller coaster, let's say, and we didn't have money to design any kind of mechanical brakes or electromagnetic brakes. So we're going to do this the easy way. We're going to make our loading platform, or unloading platform rather, at a position where the train will just stop on its own. Right? So I want to find the height that I would need, find the height of the platform so that the roller coaster comes to a complete stop. Would that be possible to do that? In theory, couldn't you find a place where it would be so high in the air that it would get slower, 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 slower as it climbs that hill, and then it would stop right at the at the level of the platform? In theory, you could do that. What would happen if you just made the height of the platform exactly the same as the height of the first hill? Let's talk about that. What if you made the height of your unloading platform rather the same height as the first hill, 35 meters off the ground? If there's no non-conservative forces, what would happen when you got to there? It'd still be going 5 meters per second, wouldn't it? Because it would gain back all the original potential energy it had, but it would also have the same kinetic energy it had there. So it'd still be going like 5 meters per second, which is over 10 miles per hour, so that's no good. You're going to have to make that platform a little bit higher than that, right? That's what we're after. How high would you have to make it such that when it goes up there, it actually comes to a complete stop at that point? What's the height off the ground? All right? So, let's call that position 3. And we'll leave this up to Meghana. Do you want to go from position 1 to position 3 or position 2 to position 3 when we do our P whatever plus KE is equal to? Yeah, it doesn't really matter. The total energy is the same at 1, 2, and 3, so we can either go from 1 to 3 or 2 to 3. Meghana said let's go from 2 to 3, so we're going to say PE2 plus KE2 is equal to PE3 plus KE3. The beautiful thing about energy conservation is that, does it really matter what happens between position 2 and position 3? Does that matter at all? What if there was a loop in there between position 2 and position 3? Would that change anything? No, the beautiful thing about it is all that matters is starting position and ending position, because the total energy has to be the same at both places. All right, so Meghana, since you took us in this direction, anything that's 0 that we can cross out, get rid of? All right, you're going to make position 2 your reference platform, which makes sense because that's the lower of the two positions. And anything else? Right, Kyle? KE3, because we want the thing to stop when it gets there. That's right. We don't want to have to use the brakes. The idea is this thing's going to get up there, it's going to stop, and at that point the ride operator just grabs the thing so it doesn't move around when the people get off. Right? Low budget. So KE2, that's 1/2 m V2 squared equals PE3. That's MGH3. Get rid of the masses. 1/2 V2 squared. Well, V2 we already figured out. That was 17.9 meters per second at the top of hill 2. So that has to equal G, 9.8 meters per second squared, times H3. And let's see what we get. If we do 1/2 of 17.9 squared and divide it by 9.8, looks like about 16.3 meters. So if you're the engineer, you're going to tell the contractors, hey, make that platform 16.3 meters off the ground. Is that going to do it? All right, Nick, what's wrong with that? You've got to add 20 meters to it because that's 16.3 meters above our reference platform. And the reference platform was 20 meters off the ground. So 20 meters plus 16.3, we're going to make it 36.3 meters off the ground. In theory, if you do that, it's going to get slower, 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 slower. Stop, ride operator grabs it, everybody gets off, everything works fine. Now, in real life, what would happen? Because there actually are some non-conservative forces here, right, Jack? It wouldn't make it to the top. It might make it to right about here. And then what would happen if it stopped right there? Yeah, then it would go back all the way through the track, maybe get to about here, and then it would go forward and do that all, well, not all day, but it would take a while until eventually it would lose enough of its energy to come to rest at the bottom of one of those hills, which is why they don't do it that way. That'd be nasty. And while we're talking about roller coasters, if you're like me, when you're in line to get on a roller coaster, you're thinking about which car do I want to get on in the train? Because in reality, it's not a single car, it's an entire train. And there's some people that like to ride in the front of the train, there's some people that like to ride in the back of the train, there's some that like the middle. And as a physics teacher, I always find it interesting to hear people's conversations when you're waiting in line. And occasionally you hear something like this: "Let's get in the back, it's faster." That's kind of funny, isn't it? It's a train, isn't it? Is it possible for one part of the train to go faster than the other? Not unless something unhooks, right? Which wouldn't be good. All right, so if the speed's the same everywhere, and it has to be, is there a reason for preferring one part over the other? Okay, you can see better in the front, that's true. Clear view, nothing obstructing you. What? Ah, okay, if somebody throws up, yeah, if you're in the back, you could be wearing it, that's true. But I tell you, I like to ride the back. I like given the choice, I'll take the very back car of the train. Anybody else like the back? All right, here's my reason for liking the back. You got to think about this. The actual train has some length to it. So when we talk about the highest point or the lowest point, is the entire train going to be at the top of the hill at the same time? No, so which part of the train should we be looking at for when we have maximum potential energy at the top of the hill? Yeah, wherever the center of gravity is, right? And as long as the thing's evenly loaded, the center of gravity would be right in the center. So the train's going to have maximum potential energy when the train is in this position right here. Right? But in that position, part of the riders are already on their way down. Some of the riders are still on the way up. Now here's why I like the back. If I'm sitting back here, in that position, this train is just getting ready to start speeding up. Everybody agree with that? Because the center of gravity, which is right in the middle, is just ready to start getting lower. So by the time I get to the very top of the hill, the thing's already moving pretty fast. And then you kind of get whipped over the top of the hill because the speed's already increased. Whereas the people in the front of the train, right, they're already over the top of the hill, starting to move down before it ever starts to gain speed. And to me, that's not as much fun. I like the acceleration you feel as you get whipped over the top of the hill at a higher speed. And the other thing that happens is down at the bottom of the hill, and this is more psychological than anything else. The center of gravity is at the very, very bottom when it has the highest speed that it ever has. You agree with that? In fact, you can tell that the fastest point on any roller coaster track is just where the track is at its very lowest position, right? Because the least potential energy means the greatest kinetic energy, because the total amount always has to stay fixed. So it has to have the greatest kinetic energy when the center of mass is at the very lowest position. But see, here's what happens psychologically. If I'm sitting in the back, I'm thinking, wow, I am flying, and I still have further to drop. Right? Because I'm looking down towards the bottom of the track. Now, am I ever going to get any faster than I'm going right there? No, but my brain doesn't know that. Whereas if I'm in the front of the car, front of the train, that's where I'm going the fastest, but I'm thinking, bummer, I'm already going up the next hill. So I think there's some psychological and excitement reasons maybe for wanting to ride one place or the other, but it's not like there's a faster place and a slower place. Here's something else that comes up sometimes. When you're designing a roller coaster, does every hill of the roller coaster have to be smaller than the one before it? No, it doesn't. You can have a roller coaster designed where you have a small hill followed by a larger hill. That's okay. You just got to make sure that no hill is higher than which one? Then the first one, because that's where all the energy is coming from. Now, actually, you can make it slightly higher if the train's moving at the top of the first hill, because it has a little kinetic energy. But usually the kinetic energy up there is so minimal that you got to make sure everything's smaller than that first one. One little graphic to leave you with here. This is not a roller coaster, but it's a similar kind of situation. Kind of like a ski slope. There's a box sitting at the top of the ski slope. And down here at the bottom we have a couple meters. The one that says capital U, that's the potential energy. Capital K is the kinetic. Capital E is the total energy. So how fast is this thing moving right now? 0, because there's no kinetic energy. It's all potential. As this thing goes down the ramp, you expect to see the potential energy meter do what? Go down while the kinetic increases, while the total energy does what? And that's the key. That total energy meter always stays constant. So as this thing goes rolling down the ramp and flying off, that total E, always the same. All that fluctuates is the kinetic and the potential. Even after it leaves the ramp, always the same total amount of energy. All right, well, in terms of WebAssign, the next WebAssign, not the one that's due tonight, is going to give you some practice working with energy conservation. The one that's due tonight just has you calculating potential energy and kinetic energy and using the work energy theorem. But the next set, which I've set to be due Thursday night, has you working with conservation of energy. Right?